New pictures obtained by the James Webb Space Telescope have stunned researchers. Rather than expanding our perception of the universe, these pictures revealed a disturbing reality. Our ongoing comprehension is lacking in grasping the vast possibilities of the universe's early stages. The hypothesis of the universe's beginning appears to be at its limits, prompting us to explore new theories about its origin. A fundamental question arises: how was the universe formed comprehensively, and why does this new revelation challenge even the most experienced space specialists? The challenge lies in understanding the Big Bang and the evolving nuances of this discovery. We should reassess the possibility of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion within pre-existing space. Instead, space itself began around 13.8 billion years ago, alongside matter and time, from a remarkable characteristic in actual science and cosmology. A singularity describes a point where gravity is so immense that the curvature of spacetime becomes infinite. Today, billions of years after the universe's inception, we understand that our celestial home is part of a significant cooperation among experts. This points to an essential aspect of the universe: its continuous development. It is important to realize that the universe is not wandering into pre-existing space. Rather, space itself is expanding in size. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first radiant heavenly objects clustered to form mature galaxies. However, how quickly these galaxies developed remains an ongoing mystery. A major breakthrough emerged with the first pictures captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected various galaxies, some of which had existed around 300 million years after the formation of the universe. However, compared to the celestial structures that formed billions of years later, these early galaxies were considerably smaller and less massive, fitting well within the accepted scientific model. The density of matter in the young universe was simply not sufficient to create galaxies of the size we observe today. This discovery began with the identification of 6 extraordinary redshifted radiant spots by the James Webb Telescope, which led to one of the most significant astronomical crises of recent times. While these newly discovered galaxies were similar in age to previously recorded worlds, they were nearly as massive as our Milky Way galaxy. This created an intriguing mystery in cosmology. After examining a series of pictures taken by the near-infrared camera, experts identified these light sources using redshift. Specialists confirmed that the light from these objects took more than 1 billion years to reach Earth, indicating that these structures existed between 570 and 700 million years after the confirmed Big Bang. Remarkably, these galaxies were so enormous that they defied conventional cosmological assumptions. Instead of finding the expected dwarf galaxies, structures were identified that were almost as large as our own Milky Way galaxy, despite their early formation in the universe's history. Upon further analysis, it was found that this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one galaxy possibly approaching 10 billion solar masses. However, even if this possibility is considered, the mystery remains unresolved. If true, it would mean that the early universe contained far more vast mass than previously anticipated, raising more questions. These objects challenge almost all conventional cosmological theories. Even if only one of these galaxies is confirmed, it would challenge past assumptions and force a reconsideration of the early universe. To explain this phenomenon, the density of matter in the early universe would need to be several times greater than previously believed. Another potential explanation is that these galaxies may have formed in a way we currently do not understand. These discoveries and the resulting discussions will undoubtedly lead to further examination of the Big Bang theory. Many space experts with alternative views are frustrated, and their perspectives often appear in scientific journals. However, even those who still defend the Big Bang theory are continually confronted with unanswered questions. These inquiries include fundamental issues such as why and how something could have literally risen out of nothing 13.8 billion years ago. Could something truly start from nothing, or was there some triggering event? Was it all just a mishap? Stephen Hawking pointed out that the nature of time as we know it began with the Big Bang, so this process could not have been set off by something else or by an external cause. Similarly, a question arises concerning the consistency of radiation and density throughout the universe. Regardless of the direction or distance from which we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation across the universe. Modern theorists explain this phenomenon through the theory of cosmic inflation. However, various experts extend this assumption further with the idea of turbulent inflation, suggesting that inflation has halted only in certain regions, like bubbles, while continuing incomprehensibly in others. This leads to the possibility that multiple universes could form in these bubbles, each with its own unique physical laws. In this model, a big question arises: what if the universe we observe doesn't represent the total whole? What if another universe existed before our own? In this case, the Big Bang would become part of a larger cycle, with our universe being just one part of a larger, more complex structure. Within this perspective, the possibility of an eternal cycle of collapse and resurrection of the universe is advanced. However, this is not the only viewpoint presented in cosmology. For instance, in 1955, an article in NASA's Big Time suggested that there may have never been a Big Bang, and the universe has existed for an indefinite period. In this view, the expansion of the universe would not exist, and the constant improvement of matter could give the impression of consistent development. Another interesting and controversial theory emerges from quantum physics and string theory. Some experiments suggest that our universe and everything in it may be a projection or a higher dimensional simulation. While this may sound like the plot of an unconventional science fiction film, it could be linked to the Kessler scale, which measures the level of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the power of an entire galaxy, it might be able to create a perfect simulation. However, determining the reality of such a situation remains deeply complex. Exploring the depths of cosmology and the origins of our universe brings us into a domain filled with profound mystery and ongoing scientific inquiry. The new pictures captured by the James Webb Space Telescope have reignited conversations about the very fabric of our reality, challenging established hypotheses and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly and resulting in the space-time and matter we know today. This colossal event was not just an explosion within pre-existing space, but it included the earliest inception of space itself. The notion of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this early cosmic epoch. However, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how rapidly structure formed in the universe's infancy. These galaxies, detected within a few hundred million years of the Big Bang, appear surprisingly developed and massive compared to current cosmological models. One of the key questions raised by these revelations is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand drastically. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, current discoveries suggest complications in the early universe's development, which may require adjustments to inflationary models. The formation of galaxies like those observed by the James Webb Telescope forces cosmologists to rethink the conditions and processes governing the universe's early history. These galaxies, now massive and large so soon after the Big Bang, suggest a density of matter that exceeds previous estimates. The mystery deepens when considering how such massive structures could form and evolve in such a short cosmic time. Additionally, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories suggest that our universe is just one of many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One theory gaining traction is eternal inflation, where universes constantly emerge from a larger inflating space. This theory suggests that our universe could be just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas, as they push the limits of observational validation. Another provocative theory posits that our universe exists within a simulated reality, much like a computer-generated recreation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can mimic complex systems with remarkable fidelity. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising significant philosophical and scientific questions about the nature of existence. Furthermore, advancements in observational astronomy continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its remarkable sensitivity and resolution, promise to uncover even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, offering clues to its ultimate fate and the fundamental principles governing its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models like quantum gravity and string theory offer potential frameworks for understanding these key interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Quantum theories suggest that time may be evolving or even elusive at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our understanding of the universe's beginnings and evolution. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific pursuits, cultural and philosophical reflections on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration continue to drive research and debate across disciplines. The recent revelations from the James Webb Space Telescope have raised the stakes in cosmology, inviting scientists to reconsider fundamental aspects of the universe's origin. One of the most fascinating questions emerging from this data is the formation of galaxies so early in the universe's history. This challenges the existing timeline of galactic formation, where it was once believed that it took hundreds of millions of years for structures like galaxies to coalesce. Instead, these new discoveries imply that galaxies may have been forming much earlier and at a more accelerated pace than conventional models suggested. This raises key questions about the distribution of matter in the early universe. According to the current cosmological framework, galaxies are supposed to have formed from dense regions of gas and dust. However, the discovery of galaxies that appear fully formed and extraordinarily massive within just a few 100 million years after the Big Bang suggests that these regions may have been far more densely packed than previously understood. This hints at the possibility that the early universe was not as homogeneous as the traditional models assume. Scientists are also grappling with how the newly observed galaxies could have formed so rapidly. It was thought that it would take longer for gravitational forces to gather enough matter to form such large and complex structures. This newfound rapidity of galactic formation implies that there might have been other factors at play, possibly a different kind of interaction or process that enabled galaxies to grow faster than previously believed. One potential explanation that has gained attention is the role of dark matter, an invisible form of matter that is theorized to make up a substantial portion of the universe's mass. Dark matter is thought to influence the formation and movement of galaxies, but its exact properties are still unknown. The rapid formation of large galaxies in the early universe may suggest that dark matter played a much more significant role than earlier models accounted for. Moreover, these findings could have far-reaching implications for our understanding of cosmic evolution. The idea that galaxies could be much older and more advanced than expected may change how we approach the study of the universe's history. It could lead to a reevaluation of the timeline of events after the Big Bang, including the formation of stars, planets, and even life. This would be an exciting opportunity to test new theories in both astronomy and particle physics, such as the potential role of quantum fluctuations or alternative forms of energy that may have existed in the early universe. Additionally, these findings might prompt a deeper investigation into the possibility of multiverse theories. If our universe formed from an inflationary process that could lead to the creation of multiple independent universes, then this new data could provide clues about how these universes evolve. It's possible that the very nature of the universe, as we know it, is part of a much grander and more complex cosmic structure that extends beyond our current understanding. As these discoveries continue to unfold, they offer an opportunity to challenge long-standing models of cosmology, pushing the scientific community to explore new avenues of inquiry and rethink the processes that govern the cosmos. The next generation of space telescopes and experimental techniques will likely offer even more data, which could either reinforce or radically change the theories we hold about the universe's origins. This period of intense exploration will undoubtedly define the next chapter in our understanding of the cosmos.